as students, you might think that you do the experiment and then, oh, everything is done, you have results. Okay, no, you have a process to be done afterwards, and this took a long time because so we finished in 2018 the experiment, and as I told you, we recently provided our draft paper to be reviewed. So it took us 1 year to actually polish our results and everything. But personally, I think it's one of the biggest fulfillment you can have to actually get your experiment to work and even work on your data afterwards.
Time for another episode of the Cold Star Project. I am your host, Jason Kanigan, the founder of Cold Star Technologies, this data science and intelligence company, process engineering firm. And I'm here with Florian Gautier. He is a doctoral candidate. He's working on his PhD in physics and astronomy at the University of Kansas. Thanks for being here.
Thank you. Thank you for inviting me.
You bet. Well, Florian, I wanted you on specifically because you just started working on your doctorate. It's very important for me to get voices from different areas of space field on this show and not just have it be hardcore business owners or venture capitalist funded people or executive directors or university heads or something like that. I definitely want to hear from everybody, right, including students and folks who are, I mean, you're working on projects, so you know, you just decided out of the blue, kind of, to start working on a PhD at the University of Kansas. So let's start with that. What made you choose the University of Kansas, and why this program?
So I decided to go to the University of Kansas because actually I got recruited on a project itself that was between NASA and the University of Kansas, the physics department of the University of Kansas. And at that time, I was actually looking for an internship in the space industry or research. And through the randomness of life, I actually managed to find this internship, apply, got recruited, did a 6 months internship here at the university, and actually I loved a lot this project. So it just started when I arrived, and so I was offered to continue on the project and to do actually a thesis, because actually NASA was through the project funding a thesis at KU, and I thought it was a great opportunity for me to actually continue working on this project, but also have the ability to get a PhD that can help me to have a solid background in physics, because I have a background in aerospace engineering, but I always loved to do science. This is why I also did a master in astrophysics before coming to KU, and I always love to join both the engineering and the project aspect in the space industry, but also the main drivers that I think is exploration. Well, actually, the main driver for me, and this goes through mainly science.
Okay, awesome. And I noticed I've got another guest, Dr. Sanchez from Cranfield University. I'm recording with him tomorrow, and he's someone that you know. Tell
Yeah.
us a little bit about that connection.
So yeah, so actually my school's years were a bit uh, special, I would say, because so I started an aerospace engineering diploma in France, in ISAE-SUPAERO, and actually we have this practice to have a gap year to either get experience through different internship during your year, or like me, actually go somewhere else, another university, to try either to have a specific master or try just something different. And this is what I decided to do. This is why I went to the UK in Cranfield University, where Dr. Sanchez is actually a professor in charge of astrodynamics and other classes. but the one I took was astrodynamics, and it was a great opportunity for me to actually work on a lot of projects, group projects with other students, and specifically with Dr. Sanchez, who I did my master thesis with. We started a project with other students. Actually, we're six students, in order to propose to ESA an experiment in the Drop Your Thesis program of ESA, and we got selected. So this means that for the full year, I was working a lot with Dr. Sanchez on this project, and actually after we perform our experiment, I've been working since 2018 with Dr. Sanchez on refining the results and everything in order to get something published.
Okay, so that'll be pretty neat. I'll ask him about you tomorrow when I record with him. And that's just completely uncoordinated on my part, just reaching out to different people and getting the two of you. And the fact that you booked it nearly the same days, just crazy coincidence.
Yeah.
So you, go ahead.
Exactly. I was just going to say that it just might be because we are currently where we work in the process of refining before sending our papers that got selected for publication. So this might be why we all decided to actually take the interview after this rather than the other way.
I see.
That might explain.
Right. Okay. Now you've got a couple of space events listed here in our document that we use for preparation for the show here. Tell us about those. So 2017 and something else that looks like The Last Jedi or Judy.
Yeah, exactly. Yeah, it's a pun on this. So they exist in France, but it's an international organization. It's called Space Up. It's a bit special because it doesn't organize conferences as we were used to, but they like to say unconference because the organizer just provide the actual logistics and provides rooms where when arriving as a participant, you decide to present something, organize either just a discussion or present your work. So that's why they call it unconference. I was part of Space of France, now way less because I moved to other countries, but usually you have several events or they are the link to other organizations on smaller scales that do events. They also recently got some contacts with ESA in order to organize more of those space events around Europe, and I personally participated into the organization of one edition of Space Up in 2017, as you said, in Toulouse, and it was a great experience. I met a lot of people from actually students that just started and are a fan of space to actually Airbus engineers that can provide more insight into what is currently done or what future project of Airbus there was at the time. The second association, it's more a specific event of Space Up. It's called the Last Jeudi. So Jeudi is Thursday in French.
Thursday.
And so it's a pun on word on Jedi, and it's the fact that every last Thursday of month we do a meeting all around France, and usually it would be a pub or some place where we can eat, drink, but also discuss a lot. And it's made for everyone that is that enjoys space, wants to discover space, and exchange with other people. Uh, Sometimes we try to also link through the web with the other places organizing around France this last jeudi. But it's really a great opportunity to meet other people that are really interested in space and might not be working with you if you are working in space because you want to discuss other projects or what's new in space or what other companies could be doing.
Awesome. I like that. Okay, let's hop back to the project you're working on now. So you are working on a NASA supported or funded thesis on, let's talk about miniaturized space particle detector. So tell us about that. What does that mean and what's it for?
Um, so as you know, space is not so empty. Actually, we constantly receive particles from the outer space. Magnetic field around Earth means that some of them are trapped, but the most energetic one usually get to Earth, and it's also really important for either the environment when you design a mission, but also for human life. So the ISS, for example, is constantly monitored concerning radiation. But now that we want to actually go forward, so go to the moon, go to Mars, we want to have more information, specifically information on the trip to Mars. We know some information from the surface because of all the missions that have been, also some from orbits, from all the satellites that have orbited or are still orbiting. But actually, the trip between those, most of the time, the payloads were off,
Hmm.
so this was not studied so much. The issue is the fact that um, you don't want a specific mission to be dedicated to only this, and the idea of NASA is that it would be interesting to have um, a small detector that is able to still work in a great range of species, so different ions, but also with different energies in order to, well, for them, radiation is really important. For scientists, it's to understand the environment that relates to the sun activity, but also to cosmic activity, and provide more data because currently we mostly have information on protons and electrons, which are the main particles in the space field. But we want to have more, and so the idea is to, because technologies now are way more advanced than what has been done in the 90s or early 2000s. We want to have something that is really condensed into the smallest amount possible and still provide a high efficiency. And this is what we are currently developing at the University of Kansas after being selected for providing a prototype to NASA after 3 years of project.
Hmm. So what kind of components are you using? What size of
So
items?
the idea was to be able to fit it in a CubeSat,
Hmm.
um, because first, for the test of the prototype, it could be easy to find really quickly a CubeSat where we could either be a secondary payload if it's a bigger CubeSat, or uh, even the main payload for 6U or something like that. So the idea, it won't be the usual 1U payload that you can find sometime in 3U ones, but I think 3U are quickly limited in terms of what they can provide. And so this is why it would be more adequate to either 6U, a 12 unit CubeSat. And so for now, we are not at the stage yet to have an actual fully builded prototype, but the aim would be to be able to be in payload between 6U and 12 units CubeSat, considering also all the consumption requirements and mass requirements.
Hmm. And tell us about the decisions that this detector will enable flight planners and mission planners to be able to make.
Um, so the knowing the amount of radiation you can receive means a lot of information on the shielding.
Hmm.
So we know quite a lot on the current shielding required for our geostationary satellite, because, well, we have had failures, so we know from those failures. And but the issue is for when you send actually people, you need to be sure that the radiation they don't have a later complication, or even when they come back on Earth to have complications that we don't know. So it's really, then it would be transferred to medicine, because I mean, I'm not expert into this, so I don't know what level is okay and everything. But while before we had just a mean level of particles of radiation, now we understand that actually the sun has cycles. So you might be aware of the high and low level cycles, but even into those, you have different subtype cycles, and also just bursts. And this kind of things that is interested to understand, and to understand the physics behind, to understand how they are produced, so that we can go from actually just observing them to be able to predict them, and maybe delay a mission later by maybe a few months, even if it costs a bit more fuel, but in order to protect either the material, but mostly people that might be inside those missions.
Okay, so that's good. I wanted a basic answer for the layperson, but we also got into a little bit more articulation there where I actually learned something. Does this tie into then the folks who are interested in the orbital collision prevention and that, and the tracking? Because this sounds like it's involved with space weather.
I'm not sure to have understood your
Yeah.
question on space weather. Yeah.
Yes. Does the radiation fall under that category of space weather?
Yeah, definitely.
Okay.
The radiation is space weather.
Yeah.
Space weather is actually, if you compare the raining as the drop of water as particles, and this is why you have this image of weather. And then you actually have the sun that behave differently, have different activities, and you have bursts that actually affect greatly our magnetosphere. And so the presence of particles, trapped or not trapped, and well, a simple phenomenon is auroras that we observe. And the fact that those fluctuates is not something constant means that they're changing, and so the parallel with weather. And so, yeah.
Okay, it sounds like I should tag you and Mariba Jaw, Dr. Jaw, when this comes out, because the orbital guys should be interested in this. I think it would impact the physics, I think. All right, well, let's hop to a couple of previous projects that you've worked on, give people a picture of what sorts of things master's degree students are working on. So you worked on something called the Student CubeSat project at
Yeah.
So
in my previous university in France, we have, you know, a lot of associations with technical appliance of or what we are currently learning, and one of those association was around CubeSat. So actually, it happens that it was the association actually disappeared a few years ago, so we had to restart it again, by gathering different people, finding projects to start. So the idea was really to, as quickly as possible, get older students with some expertise to be guiding newer students, and so that we could have, you know, a rotating cycle, because we are limited by the amount of time you stay in this university for the master. And so the first year we couldn't actually start a new project directly, so we decided to link ourselves with other projects that were just starting. And this is why I met Fabien Appert. I think that you had him in another interview, and we started working on CubeSat. So at the time, it was the development of a multi-mission 12-unit CubeSat that could provide for the different French university, especially the science um, universities, to have a way to access space with their payload and not focus on the engineering part of the structure itself. So I worked especially on ATISE. That was a mission focusing on on the studies of auroras. And at this time, I worked as a system engineer because we had a small team. So I was helping Fabien Appert, that was the main system engineer, but he was an engineer of ISAE-SUPAERO, so he will stay all along for the project. And this allowed me to learn a lot of things about CubeSat, about the different fields that are involved into building a CubeSat that is in one way just a small satellite. So you have exactly the same field as bigger satellites that can be produced by Airbus or Thales or other companies. And I finished this year by actually being present, actually presenting during the preliminary design review with member of CNES that were attending. So CNES is a French space agency, and it was great formation for me to actually apply everything that was academic from the classes to an actual project. And this is where I got the passion about CubeSat, where I think that it's like really, uh, a great way to enter space and a great way also to develop a new idea of space with multiple interacting and modularity of space. Um, so this was the start in my first project. I also like worked on smaller scale project. I went into coding to understand how control center worked, because at the same time we were trying to develop a multi-mission control center in the university for the future CubeSat specifically, but also to help CNES to have this kind of adaptable control center. So I worked into this, which gave me a bit of knowledge into how communication with satellites works, how do you handle packets and everything. So really great year of formation for this one.
I really like the idea of pairing the experienced students with the new students as well, and that is not only good just for academic, it's good for commercial as well, because what will happen if you don't do that is there's no knowledge transfer, and when the experienced people leave, all that institutional knowledge vaporizes, and I've seen that in many places, not just in the space field. A lot to do with manufacturing and science stuff.
Did you know that the small sat industry has a 40% and greater partial and full mission failure rate? That's terrible. And yet I find most people in the space industry try to treat this as if it's no big deal. They don't even want to acknowledge it, and I think that's ridiculous. If anything, anywhere else was having a 40% or greater failure rate, trying to turn your car on, right? If your vehicle or your cell phone didn't work 4 times out of 10, 2 times out of 5 that you tried it, you would go berserk. And you would do everything you could to make sure that it got fixed. The Small Sat Process Engineering Department at Cold Star Technologies is all about showing you how to manage processes better, to eliminate the causes at the root that create these partial and full mission failure rates. And you don't need to hear it from me. You can look this stuff up in studies. It just comes out of what you might think are the dumbest things. Oh, I know that. Well, to know but not to do means you don't know it. You rush the production schedule, you don't manage it right, you don't have the project sponsorship set up quite right, and the resources aren't there. You've got this mission launch date that's moving, and you just throw the schedule out the window. 1/3 to 1/2 of your project schedule needs to be for testing. And yet, this is the first thing to get smashed in the head by a wrench. As soon as the monkey wrench is thrown into the operation, testing time goes out the window. You want to avoid this problem? The answer is not more physical engineering. It's not. More engineers are not going to solve your problem. You have tons of engineers. I am not going to tell you how to engineer a satellite. I've got Dr. Rick Fleeter and other people on my team for that. And we're not going to come in there and tell you how to engineer it. But on the process side, and I have had engineers on this show say, engineers don't know nothing about processes. That's not me saying it, it's the engineers saying it, but I will definitely echo it. If you want to have a manufacturing process that ensures that your small sats, CubeSats, get up there and work. Come talk to us at Cold Star Tech.
You also worked on a project called Land 3U, which was about simulating CubeSat landing on asteroids. So let's talk about that.
Yeah, so as I said, with Dr. Sanchez, during my year at Cranfield, we so Dr. Sanchez, he might talk more about this, but he has a strong background in astrodynamics, and just before we arrived at Cranfield, worked on the landing, or the trajectories to have for CubeSat to actually land on the surface of an asteroid. And those papers that he produced gave one value that is really important, is the actual velocities that you could achieve when landing. So especially those ideas were developed around an ESA project that actually is also with NASA. So the ESA side is called HERA, and the NASA side is DART, D-A-R-T. So it's a mission to test the capacity to move an asteroid from its trajectory. So it's an impact mission, and ESA is providing another satellite that would observe the aftermath of the event. And one idea from ESA was to actually include CubeSats on it. And some papers wanted the CubeSat either by the end of the life or as a main goal of the mission to land on the surface of the asteroid, either to understand what material have been digged out of the asteroid from the impact, or just analyze the surface. But the issue is that landing on asteroid for such small objects is really hard, because we are talking about 3U at the time. Now it might be 6U embarked, but still, in order to have propulsion and to have active methods to land, it's really hard when you see when you compare to what Osiris will have to just get closer, or what Hayabusa had. It seems really hard. So we wanted to provide a bit more information into this, and this is why we decided to propose an experiment in microgravity to simulate the landing of a CubeSat, because we found out that most of the experiments before were actually performed with for ballistic for ballistic impact. So it was really more shell and like a sphere to impact. And the issue is that the CubeSat might have some controls of rotation and everything for its inertia, but um, it would be limited in a way, and you don't want, if you have some solar panel or something like that, you don't want to break, and you want to also target as smoothly as possible the area of interest. So we were interested into finding how characterization of this impact, and to know what it would be for a 3U CubeSat. We got selected by ESA, and in the Drop Your Thesis program. So the Drop Your Thesis program is a one-year program where ESA finance your project and get you access to the ZAM drop tower. So it's the highest drop tower in Europe that provides you almost 5 seconds of microgravity. And this allows students to actually, well, not only students use this drop tower, but this program allows students to access to it. And we were followed by ESA experts to develop, and they provided resources, contacts with different departments of ESA to develop our experiment and to be able to get results in the end. So it was a one-year work. We were 6 students, 5 master students, 1 PhD student. We managed to be on time. We completed. We did our experiments. It was really great experience um, to follow a project from the beginning to the end. To also have, only 1 year to produce something that needs to work in an environment that is so hard as microgravity, because like a lot of things that you might think would work or would be okay actually doesn't work. Just an example, we had to simulate the actual surface of an asteroid, and we worked with ESA to obtain samples that they have recreated out of all the information we have. And through discussion with experts, we all saw that by compacting enough, we would have a flat that would not um, be perturbated during the change from gravity to microgravity. However, it did not happen like this, and actually all the soil started floating around, so it's hard to get an impact inside a cloud of pebbles. So we had to on-site to find a solution to develop, and we changed actually the type of asteroid we were aiming at to more rocky ones, allowing us to actually um, make the soil more compacted and more easier to maintain. Um, but it's something that makes you learn a lot of things, especially on the experiment side of everything. And this is why you always need to be preparing so much. We have a lot of things could have gone wrong, but we prepared well, and things that we thought were prepared for actually went not as good as we thought would be. But actually, we got good results. Um, and from this we actually went through the phase of analysis that well, as student you might think that you do the experiment and then everything is done, you have results. Okay, no, you have a process to be done afterwards, and this took a long time because so we finished in 2018 the experiment, and as I told you, we recently provided our draft paper to be reviewed. So it took us 1 year to actually polish our results and everything. Really, but personally, I think it's one of the biggest fulfillment you can have to actually get your experiment to work and even work on your data afterwards.
Right, right. Yeah, great learning experience. And I'm still even more curious about what you discovered, because for our general listeners who maybe not be familiar with space, asteroids are often just a jumble of material held together by gravity and floating around out there. So as you discovered, if you try and do some sort of gravitational change or even plan for a ballistic impact, the thing just I imagine just goes into a cloud, and you can't land on a cloud. So
yeah, exactly. But no, here it was more the cloud aspect was more. So the issue is that in microgravity, you well, everything is made on Earth under gravity, and we don't see it, but actually even a table that seems flat, if you put it in microgravity, will start to bend a little bit because its own weight is not pushing itself towards the ground anymore. So those small perturbation actually makes it really hard to perform an experiment if you don't constrain your volume. So this is what happened in our experiment, where actually the soil started uh, to spread together. In an asteroid, you can have those type of phenomena. However, since the asteroid is still there, it means that what is there is already stable. So it's the end state. But this might mean that you would have a cloud forming at the beginning with a more sturdy inner core, but then it could provide more information on the time it takes for this cloud to actually rest back or escape if it escapes, and those kind of information are really interesting. We were limited for 1 year, but we worked with a lot of others um, doctors and professors in other universities that actually were interested to look at other information that could be provided by our experiment, or even trying to improve our experiment to focus on other details, because we were a team of mostly engineers. So our focus was to understand how the rebounds is affected on the surface of an asteroid in microgravity condition, especially due to the fact that we don't have a specifically flat or round object. But as you said, I mean, now maybe later there would be another team, either by Cranfield or another university inspired by our experiment, to actually perform further improving our design, because we kind of started from scratch on this, improving our design of the experiments, trying to go forward, knowing what went wrong with us, and actually look at all the details in order to prepare experiments. Yeah, and this is the kind of things that I hope might happen.
Okay, Florian, just before we leave this particular topic, I'm curious. So the end result of the CubeSat landing, quote unquote, on this asteroid, are you imagining that it's going to have little feet and it comes to a gentle landing like a lunar lander, or more like a ballistic shell that punches into the surface and stays there and then gathers data through sensors or something and sends it back?
So, so the idea is already, and this is why this experiment was possible, from calculation from Dr. Sanchez, and he will be able to explain also to you if it's part of the discussion. But the end velocity was something between 10 centimeters per second to 20 centimeters per second. This is when you give no push to your actual CubeSat, and knowing a certain initial distance, and just gravity, the small gravity of asteroid for a long time, maybe 3 hours, attracting your CubeSat makes it to have 10 centimeters per second. And so 10 centimeters per second is like a movement like this. So it's really slow. But still, the issue is on Earth, you most of the things have a rebound, but you have dissipation of energy and also gravity that is so hard pulling it back again, and actually you have micro rebounds. But on asteroids, you don't, because the tiny velocity makes actually a huge movement, not so huge to the point that you escape, but huge enough so that you can actually arrive maybe 10, 100 meters away from your actual targeted location, and that can be a nightmare for your experiment if you wanted like specific location, such as for the mission we were thinking to be as close as possible where a previous impact was done. But this impact would be like high velocity impact, but not for CubeSat.
Right. So you send out a flyer basically that creates the initial impact. Okay.
Yeah.
And the interesting thing that I just learned from you now is that you can take a considerable period of time to accomplish the landing. It's not something you want over in 15 seconds or something like that. You can spend 5 hours if that's what you really need to do to make it soft. Okay.
Well, I mean, it's gravity, because you start with an initial push that is almost zero velocity, and just by having it fall to the ground, you know, the acceleration on Earth is 10 meters per second. So every second you gain, 10 meters
9.8
square.
yes,
So every
yeah.
second you gain a velocity of 10 meters per second. So if you wait enough time, you would have a huge velocity. Here, because the gravity is so low, actually when you arrived at the impact point, you are 10 centimeters per second. But you are not like you are not 1 minute away at this velocity from the asteroid itself. Like the MOSA spacecraft that is delivering the CubeSat might be 200 meters away or something like that. So when you imagine that your final velocity, not initial one, is 10 centimeters per second, it takes a long time to arrive. And the issue is that the same when you go when you have a rebound, even if you dissipate half of your velocity, you still have a 5 centimeter per second, and with this low gravitational that attracts you back, it needs a long time to actually get a vertical velocity to get to zero, and then again, and you don't rebound vertically, so you don't stay in the same position, but actually have, you know, a ballistic a curve. So this is why you can get 100 meters away from your initial points.
Right, where your imagined target was. Well, now you've got me wondering about terminal velocities for different masses. That's something I haven't really thought of before. Just Earth in my own physics studies. Okay, well, let's fast forward to a few years from now. You've got your PhD. Artemis has brought us back to the moon. We're learning a lot about lunar construction, fuel provision, and that. And I'm curious, and this is just a snapshot as of today. I understand ideas change over time and that, but where do you see yourself, or where do you hope to apply what you've learned in your skills?
Well, depending on the amount of time it takes us to get there, I might not have exactly the same um, role into those kind of things, because I really enjoy to have a global view on the project, and and for sure I might start focusing on one aspect of a mission, but maybe in 20 years I hope I would be on the global scale of the full mission. So considering those things, I think it's really interesting um, how compared to a normal mission where we send something out and we just let it go, sometimes a bit more complicated, we need to think about retrieving something, but those mission needs to form an ecosystem kind of, because you need to have continuous interaction links with moon base if there is, as there is now with the ISS. You cannot like just design a one way to go. You need to think of the return, and usually you don't want it to be just once, because if it's just once, the cost is tremendous, and you don't want to spend so much for this. So through different projects in my curriculum, we had student projects, you know, group projects where we design some moon base, some ideas on the use of fuel and everything. And really, the complexity of those kind of things, I think, is, for me, it's a challenge that I would really like to undergo and to tackle. But it really depends, because I know that in the few years from now, I might be more interested into uh, missions that are for exploration, because as I told you earlier, it's my main driver is science and exploration. And it's true that even if there's still things to learn about moon, about Mars, it's more in itself an engineering challenge rather than the science idea. Well, science will be everywhere, and we will get as much information we can as secondary payload on whatever mission we have on the moon. But it might be specifically more on the human side part. So I think like you will have a medicine branch that will like uh, skyrocket, that would be space medicine. Uh, but for the near future, and I think so, this would be moon base time. I would be more focusing on actually continuing exploration, such as, you know, icy moons, exploration in the solar system, because I think they get all the information we're currently lacking from our system, and even continuing to look for life if it exists in our system. But maybe like later on, I would greatly enjoy uh, to work on this on a global scale, you know, of how to maintain, maybe at this time it would be between the moon and Mars or something like that, you know, working on this global system would be great.
All right. Would you prefer to work for government or commercial, at least out of the gate?
That depends on how commercials evolves,
Yeah.
because most commercials have been in the previous years not so taking the step forward, but more following the requirements given by a government agency. Government agency were pushing things forward, mostly developing the technologies. Then those technologies were given, or companies were started out of it. NASA developed everything that is known about the different profiles of planes that allows now the big companies to be able to have reference into which type of wings you need to use. And I don't know, but for me it seems something more pure to go for. So this is why I would say government agencies, but also, you know, with even if we still have the commercial, but with new companies, you might have like companies that would go forward into asteroid exploitation or providing. I've learned, you know, I went to the International Astronautics Congress, and you have a lot of companies that even if for now you don't have you don't have government agencies that specifically ask for a design for this, they are starting of thinking multi-mission designs to go exploration and all kind of things. And this might be commercial companies that I would work for, definitely.
All right. Well, Florian Gautier, PhD candidate at the University of Kansas. I've really been enlightened by your perspective. It's been fun to have you on. Thanks for being here.
Thank you. Thank you very much.
This is Jason Kanigan from Cold Star Tech. Thanks a lot for listening to this episode. I hope you enjoyed it. If you do want to get email notifications of upcoming episodes or episodes that have just been released, and maybe a little news sprinkled in here and there, you can sign up for email notifications at coldstartech.com/MSB. That's short for Make Space Boring. That's another little show that I do. It's once, twice, 3 times a week, something like that. Anytime there's news or an update on who I'm meeting and what I'm studying in the space field. So you can go check that out. On the YouTube channel, I can do something that I cannot do on Anchor for the audio only side of things. The YouTube channel allows me to have playlists, and so you might want to go to the channel, the Cold Star Tech channel, and check out those playlists, because you will find you can go down a rabbit hole basically into several areas like space law and policy, small sats, and I think that's a lot easier than trying to scroll through 130 episodes or something like that, looking for the thing that you want. So I recommend going and checking that out. And remember, if you're ready to take your space business to the next level, or you're a VC looking for deep and very valuable insight into a space company you're looking at investing in or investing further in, come and talk to us. Thanks for listening.